To date, no form of life, neither past nor present, has been definitively confirmed on Mars. All evidence gathered so far is indirect or suggestive, and scientists continue to probe the planet for signs that microbial life might once have thrived there, or perhaps subsists even now in hidden niches. Below is a summary of what we know and what remains possible. 1. No confirmed extant life. Despite decades of robotic exploration, from the Viking landers in the 1970s to today's Perseverance and Curiosity rovers, no experiment has yielded an unambiguous detection of living organisms on Mars. Instruments have found organic molecules and transient methane plumes, but these could arise from non-biological, abiotic processes such as ultraviolet breakdown of carbonates or geological outgassing. 2. Evidence for a watery past. Multiple lines of evidence indicate that ancient Mars was once warmer and wetter, featuring rivers, lakes, and perhaps even a northern ocean. Curiosity's analyses of sedimentary rocks in Gale Crater reveal ancient stream beds, wave ripple structures, and minerals, like clays and sulfates, that only form in the presence of liquid water. Such environments on early Mars, 3.5 to 4 billion years ago, could have been habitable for microbial life, as they provided energy, nutrients, and protection from harsh surface radiation. 3. Organic molecules and complex carbon chemistry. In 2025, scientists reported the detection of the largest organic molecules yet found on Mars. Rich, carbon-bearing compounds embedded in powdered rock brought up by Curiosity's drill. While organics are the building blocks of life, they can also be generated and preserved through purely geological or chemical processes. Nonetheless, this discovery expands our view of Martian prebiotic chemistry and suggests that, at least in the past, Mars had the ingredients necessary for life. 4. Signs of an ancient carbon cycle. Recent work has uncovered siderite, iron carbonate, in sulfate-rich layers of Mount Sharp. This indicates Mars once had a global carbon cycle, akin to Earth's, that could cycle CO2 between atmosphere, oceans, and rocks. A robust carbon cycle implies a climate capable of sustaining liquid water long enough for biological processes to take hold, bolstering the case for ancient microbial ecosystems. 5. Methane and transient gases. Orbital and rover missions have intermittently detected trace amounts of methane in the Martian atmosphere. On Earth, a substantial fraction of methane is biologically produced, e.g., by microbes in wetlands. On Mars, however, methane could also arise from reactions between water and certain rock types, serpentinization, or be destroyed quickly by ultraviolet radiation, accounting for its fleeting presence. 6. Potential modern habitats. Even today, Mars may harbor refuges for hardy, extremophile-like microbes, subsurface ice and brines. Radar data suggest patches of liquid water mixed with perchlorate salts beneath the poles and in mid-latitudes. Brines can remain liquid down to -70 degrees Celsius and could host microbial metabolism. Deep aquifers. Geological heat from Mars' interior might maintain pockets of liquid water several kilometers underground, protected from surface radiation. Recurring slope lineae, RSL. Dark streaks on crater walls appear seasonally and may involve transient flows of salty water. Mars sample, return. Rocks with evaporate layers and subsurface brines are prime targets to search for fossil or extant halophiles and endoliths. Instruments like Sherlock and Pixel on Perseverance aim to detect organic biomarkers and microtextures consistent with these niches. Life detection strategies. Focus on cryptic habitats, beneath translucent salts, or within rock pores, using drill-mounted Raman and fluorescence spectrometers to target pigments, e.g., carotenoids, chlorophyll derivatives, and cell wall signatures. Future drilling, proposed missions, e.g., Icebreaker, ExoMars, Rosalind Franklin, with deeper drills, greater than or equal to 2 meters, could access stable subsurface brines, where halophiles might reside dormant. While no definitive Martian organisms have yet been discovered, Earth's halophiles and endolithic cyanobacteria demonstrate remarkable resilience under conditions paralleling those on Mars. Their survival strategies, osmoprotection, radiation repair, perchlorate metabolism, and endolithic refuge, make them plausible candidates for extant or preserved life in Martian briny niches and evaporitic deposits. Ongoing and planned missions use these analogs to refine biosignature detection, ensuring that if halophiles or endolithic cyanobacteria ever existed on Mars, we have the tools to find them.